determine the efficiency of a reaction. You need two numbers to determine the percent yield. You need the actual yield. So if you're actually doing a lab and you made an amount of product, the mass of the product would be the actual yield. That's how much you actually get of the product if you're running the reaction. The theoretical yield is the amount of product that you could get under ideal conditions. You would use stoichiometry to do these calculations. You've actually already done this calculation in a limiting reactant equation. Whenever you do step 2 and figure out how much of the product you should get, that's the theoretical yield. You're never actually able to get 100% percent yield because conditions are never perfect. They are never ideal. You also can't get more than 100% yield because that means you have something other than the product in your product. It's been contaminated with something else, or the reaction hasn't gone all the way to completion. Between 80 and 100% is a pretty good yield. Percent yield is a ratio of the actual yield to the theoretical yield. That means you're dividing the actual mass divided by the theoretical mass times 100. This is the problem from your notes. Iron is reacting with oxygen to form iron 3 oxide. You're given 25 grams of iron. That's your starting mass of the reactant. It reacts with oxygen, enough oxygen that you won't run out of oxygen, to produce 29.8 grams of iron 3 oxide. So this 29.8 grams, that's how much they produced when they actually did the equation. So that's our actual yield. We have to calculate theoretical yield using stoichiometry. So we need to figure out, if we start with 25 grams of iron, how much iron 3 oxide could we theoretically produce? And you already know how to do this. So we put our 25 grams over 1. We convert it to moles. We do the mole ratio step where we're going from the moles of iron, the reactant, to moles of iron 3 oxide, the product, and then you go to the mass of iron 3 oxide. So that tells us we should get, under ideal conditions, which never happen, 35.7 grams of iron 3 oxide. The only new part here is now we're dividing the actual mass from the problem, 29.8 grams, divided by the number we just figured out, the theoretical, times 100, tells us that our reaction has an efficiency of 83.5%. Here's one more problem. This one was not in your notes. This is calcium carbonate. It decomposes when you heat it to calcium oxide and carbon dioxide. Here we're starting with 24.8 grams of calcium carbonate, and we're decomposing it. And when they actually did it, they got 13.1 grams of calcium oxide. So that's our actual. We have to figure out the theoretical. So you start with 24.8 grams of our reactant, calcium carbonate. Do this math that you already know how to do. So we convert it to moles of calcium carbonate. You do your mole ratio step, and then you go to grams of the product. I got 14 grams of calcium oxide, so that's my theoretical. Now I just divide my actual from the equation, for the problem, 13.1 grams, divided by the number I calculated, 14 grams times 100, gives me a good efficiency, 94%.